We are going to see the load balancing concept. I am Professor Sri Krishna Gosavi, Assistant Professor, Department of Civil Engineering, WIT Solapur. So the learning objectives of this is, at the end of this session, students will be able to analyze prestressed concrete members by load balancing approach. Now what is load balancing concept? So this is a typical section of a member, the longitudinal section along the length. This is the centroidal neutral axis. This is the bend tendon which is provided in the prestressing. Basically three types of tendons are provided. One is the straight, second one is the parabolic, and third one is the bend tendon. Now here the bend tendon is shown. Now the prestressing force is applied to the bend tendon. This is the span of the beam. Now the eccentricity of the bend tendon is maximum at the center, that is eccentricity E, and this eccentricity at the end is 0. You can see in the diagram. Now let us say that this angle is theta. Okay, the angle of bend tendon with the centroidal axis is theta. Now you can see by alternate angle theorems, if above two angles are theta, then below these two angles will be also theta. Now suppose the external load is acting on the beam. Now here it is the UDL first. UDL means self weight of the beam. This is nothing but the self weight of the beam. I have considered the SI units, so I have taken it in kilonewton per meter. It may be in Newton per meter also, Newton per mm also. So now this is the self weight which we considered as a UDL. Now this is the point load which is acting at the center of the beam. Let us say that it is a W kilonewton. Yeah. Now here you can see, due to this external prestressing force, here is the prestressing force applied from this end, the prestressing force is applied from this end, due to which in the tendon internal restoring force is getting generated of the equal magnitude, and that force is shown over here in both the bend tendons. Okay, and this force P, it is inclined at an angle theta. So now you can see, as the theta is very small, this theta is the acute angle. Now we can resolve this force P. So if I resolve it, then see there are two components. One is horizontal, other is vertical. Horizontal component is P cos theta, vertical component is P sin theta. Similarly on this side also, if I resolve this P, again I will get two components. One is horizontal, other is vertical. Vertical is P sin theta, horizontal is P cos theta. Now these two P cos theta are acting in the opposite direction. They may cancel each other. Now you can see P sin theta and P sin theta, these two forces, and these are exactly acting at the center. Okay, at a distance of L by 2. If the total span is L, then this will be L by 2 and L by 2. And these two P sin theta forces are resisting this W kilonewton force. It is acting downward and these two are acting upward. So now see, as theta tends to 0, theta is very small, we know that sin theta is nearly equal to the tan theta. And now if you consider any of this triangle, if this triangle or this other triangle, okay, if this angle is theta, from here to here the length is L by 2 and this is L. Now if I use tan of theta here, then opposite side upon adjacent side, so it is E divided by L by 2. As tan theta is nearly equal to sin theta, I can put this value, sin theta is equal to E upon L by 2. Now here you can see the total upward load. So here P sin theta which is equal to 2P sin theta, which is total upward load. Total downward load, this is the point load, W kilonewton. So we can calculate net downward load. Net downward load is the algebraic sum of this. So it will be W minus 2P sin theta. So the bending moment due to the above net downward load, that bending moment is M is equal to, see this net we need to consider, W minus 2P sin theta into A into B divided by L. This formula is the formula for a point load which is acting on a beam, generalized formula, WAB by L. So instead of W, here we are considering net load, W minus 2P sin theta plus WL square by 8. Now this WL square by 8, it is for this self weight. Okay, suppose the sulfate is W, then it will be WL square by 8. This is the bending moment for the sulfate. This is the bending moment for this net load. Okay, now once you calculate the bending moment, we are going to calculate the stresses, direct stress and bending stress. So direct stress is P by A. It is always considered as positive because we are taking the sign conventions as compressive stresses are positive, tensile stresses are negative. So direct stress is always a compressive stress, so it is positive at both the sides, above the neutral axis as well as below the neutral axis. And the bending stress, here you can see the bending stress M by Z, it is plus minus. Now why it is plus minus? So it is plus at the top, okay, above the neutral axis, and minus at the bottom below the neutral axis. Means if the net load is coming, it is downward, then the profile of beam will be the hogging profile, sorry, sagging profile of the beam will be the sagging profile, and the fibers above the neutral axis are subjected to compression, fibers below the neutral axis are subjected to tension. So that is why at the top we are considering the positive sign and at the bottom we are considering the negative sign. So if we calculate the resultant stresses, then resultant stresses will be, here you can see the resultant stresses, P by A plus minus M by Z is the resultant stresses. So resultant stress at top P by A plus M by Z, and resultant stress at bottom P by A minus M by Z. Okay, this is what is when the point load is acting at the center of the pre-stressing concrete beam. Now if you see the same concept, but now we are taking external UDL. Now here you can see the UDL is acting on the beam, okay, and sulfate is also there. Now this type of tendon, this is the parabolic profile tendon, this is called as parabolic tendon. The span of beam is again L and pre-stressing force is P applied over here. Now again see, the member carries a external UDL in addition to its sulfate. So sulfate also you need to consider additionally over here. Let's say the UDL is W, then E is the maximum eccentricity of the parabolic tendon at the center. So now we know this. The bending moment due to pre-stressing force, it is P into E, load into eccentricity. Bending moment due to this external load, it is WL square by 8. If we equate these two, we will get the equation WL square by 8 is equal to P into E. Now we want the value equal to W, so that we will get the upward force. So now here this WU, that is the upward load, it is 8 PE upon L square. So this is your upward load. Okay. So now net downward load is W minus WU, that is W minus 8 PE upon L square. This is your net downward load. Now this we have already discussed, net downward load W minus 8P upon L square. Now bending moment due to the net downward load. So this is the bending moment WL square by 8, where we are considering this net load. So in this W here I have considered the external load as well as the sulfate of the beam. See, external load is also given as a UDL and sulfate of the beam is also UDL. So you can take the total load over here, both are acting downward, and from that minus this 8PE upon L square. So you will get the net downward load into span square divided by 8. Now after the calculation of bending moment, we are calculating the direct stress and bending stress. So direct stress, it is P by A, as we discussed earlier, it is always compressive, plus P by A. Bending stress is equal to M by Z, it is plus minus, as the net force is downwards, so beam will sag, and in the sagging profile compression is at the top, so plus is at the top, tension is at the bottom, so minus sign is at the bottom. Now the resultant stresses, here you can see it is P by A plus minus M by Z. So the resultant stresses at top P by A plus M by Z, resultant stress at the bottom P by A minus M by Z. Now we will go quickly through this problem. See, a pre-stressed concrete beam of cross section 400 mm by 600 mm is provided with inclined tendon having 0 eccentricity at ends and 100 mm at center. The beam carries a point load of 160 kN at its center. The span of beam is 6 meter. The dead load of beam is 6 kN per meter. Determine the extreme stresses at midspan section of the beam by using the load balancing concept. The pre-stressing force is 1000 kN. So here the diagram is already drawn. This is the section, 6 meter is the length. there is a bend tendon is provided. So here eccentricity is 100 mm. So if this total is 6 meter, then half of that is 3 meter, pre-stressing force is 1000. Now this is the self weight, okay, 6 kilonewton per meter. Here they have given us the self weight in the problem, the dead load of the beam 6 kilonewton per meter, that self weight we have considered. Then here is the point load. This point load is of the 160 kilonewton at the center. So the value of this point load is 160 kilonewton. Now we can calculate the upward load transmitted by the cable. It is by 2p sin theta. We have already seen upward load how to calculate. Now it is 2p sin theta. If you put the values, you will get that net upward load as 66.66 kilonewton. So after that, net downward load can be calculated. So net downward load is, now upward load is 66.66 and downward point load is 160. So if you do the algebraic summation of that, that is 160 minus 66.66, the net downward load works out to be 93.34. Now again, the bending moment at the center. So it is now due to this dead load as well as this point load. So for the point load, the formula is PAB by L or WAB by L, plus for this UDL, it is WL square by 8. Now just we need to put the values in this formula. So here our net downward load is 93.34 into 3 into 3 by 6 is the span, plus WL square by 8. W is 6, this is the self weight, 6 dead load, into 6 square by 8, and that value works out to be 167.01 kilonewton meter. Now extreme stresses calculation. So as we know, direct stress and bending stress we need to calculate. So the resultant extreme stresses are P by A plus minus M by Z. So here again the values we have kept. So the value of P is 1000 into 10 raised to 3 divided by area. Area is 240 into 10 raised to 3. The area comes from the cross section. The cross section of the beam is given as 400 by 600. From that we can calculate the area. Again plus minus, here the M value in the previous slide we have seen, it is 167.01 kilonewton meter. It is converted into Newton mm. That is why it is 10 raised to 6 divided by Z. Z is the section modulus. It is 24 into 10 raised to 6. So Z for the rectangular section, we know Z is the section modulus. The formula is I by Y, moment of inertia divided by the distance of the extreme fiber. Now for the rectangular section, Z is equal to BD square by 6. Okay, so BD square by 6, so 400 into 600 square divided by 6. If you calculate that, the value you will get is 24 into 10 raised to 6. So for this P by A, the direct stress works out to be 4.17 MPa, megapascal, Newton per mm square, and the bending stress is 6.95 MPa. Then the stresses at the topmost fiber. The stress at top is P by A plus M by Z. So it will be the addition of these two, 4.17 plus 6.95. It works out to be 11.12 MPa, Newton per mm square. And we got here the positive value. That is why we say that this stress is the compressive stress. So the fibers above the neutral axis will subject it to the compression, and the extreme compressive stress at the topmost fiber will be 11.12 Newton per mm square or megapascal. Similarly, the stress at bottom is P by A minus M by Z. So again, if we do the subtraction of these two, 4.17 minus 6.95, it works out to be minus 2.78 Newton per mm square or megapascal. So minus sign indicates that at the bottom fiber of the beam, the force is tensile. At the bottom fiber of the beam, the stress is tensile stress. So in this way, we can calculate the stresses induced in the prestressed concrete beam, the resultant stresses at top, the resultant stresses at bottom, by using the load balancing approach. So these are some references. These are good books. You can refer this. These are some references which I have referred. Thank you.